Yeah, hi students, welcome to iitiansgateclasses. Gate classes. Hi, I'm Nikhil Agrawal. I'm a graduate from IISc Bangalore. I did my MTech research in computer science and automation department. So I hope the preparations are going well. So today we will be covering the previous year questions related to operating system and then followed by subjects related to computer networks. Okay, yeah, so we will be covering the questions related to uh, like we will be covering the previous year questions that has come in the year 2023. Okay, so yeah, let's get started, students. Yeah, so first question is, which one or more of the following need to be saved on a context switch from one thread of a process to another thread of the same process? Okay, so we all know what are threads. Threads are lightweight process. Okay, threads threads are, come on, threads are lightweight process. Okay, so in this case, uh, so there are, for a particular process there can be multiple threads. So in this case what they're asking, like, if there is a context switch happening among the threads of the same process, so which of the following needs to be saved? Any idea? So will they be sharing the page? So is there any need of saving the page table based register? No, because threads will be like they are page table we are having at the process level. Okay, so we don't require page table based registers to be saved. Okay, stack pointer, yes, like each thread has its own stack. So yeah, stack will be there. Program counter, yes, each thread has its own program counter so that they can determine then what is the address of next instruction to get executed. So yeah, program counter will be there. General purpose registers, yes, again threads have their own registers. So yeah, this is also the part. So yeah, the correct options are B, C, D. Okay, good. Yeah, let's move on to the next question, students. Yeah, which one or more of the following options guarantee that a computer system will transition from user mode to kernel mode? Okay, come on, try. So there is a word guarantee over here. Okay, come on, let's think. So function call. If I'm doing a normal function call, is it guarantee that the transition will happen from user mode to kernel mode? Is there a guarantee when I'll be doing the transition from user mode to kernel mode? No, because it can be a normal user-defined methods also. So in that case, it doesn't guarantee that there will be a transition to kernel mode. Okay, yeah, come on. Let's discuss the option page fault. We all know whenever there's a page fault happens, OS comes into the picture to handle that page service. Yeah, so in that case, if OS is coming, so definitely there's a change of mode from user mode to kernel mode. Okay, so that's why page fault will guarantee that computer system will be switching from user mode to kernel mode. Okay, system call, system call. Come on, students, system call. Yes, whenever we do a system call, let's say doing fork system call, so it will always guarantee that a computer system will transition, like it will be going to the kernel mode. Okay, malloc call. Any idea, guys? What does malloc does? Malloc allocates some amount of memory. Let's say if you are allocating some 4 bytes of memory, you give that parameters, and then accordingly we will be getting those values. Okay, now malloc call. So can I say that in like if you're thinking that malloc call will transition from user mode to kernel mode, are you thinking that Arshan, okay, whenever we're doing malloc call behind the scene, there's a system called SBRK that will get called. Yes, come on, students. Yeah, just a minute. Yeah, sorry for the interruption. Just a moment. Yeah. Yes, yeah. So when we are doing the malloc system call, is it always necessary that there will be transition to the kernel mode? No. Why? Say if I want 4 bytes of memory. Okay, so internally malloc, how it happens, like it will be calling some another system call that will give me not only 4 bytes, it may provide me the memory at the page level. Okay, so let's say if I'm requesting for 4 bytes, so that may allot me some granularity. So let's say it may allot me 1 kilobytes. Okay, it won't be returning as 1 KB, but internally I got 1 KB, so that whenever next time if I'm calling malloc with some number of bytes, So that time I don't need to call the function call. So that's why I'm saying that malloc call doesn't guarantee always that there is a transition from user mode to kernel mode. Okay, so that's why in this case the answer is C and D. Okay, yeah. Yeah. So again, next question. Which one of the following CPU scheduling algorithms can potentially cause starvation? Come on, students. Which of the following CPU scheduling algorithms can potentially cause starvation? Let's talk about first thing. FIFO, first in, first out. Say if there is a process, if there is a process, okay, that will actually, that has a very large burst time. Okay, that has a very large burst time, close to infinity, you can say. So will other process get chance to run? In this case, no. So that we can say that it is causing starvation, like it's occupying CPU so many times, so much amount of time that other are unable to use. So FIFO can cause starvation. Round robin, no. Every time, like we'll be having some time quantum for which the C process will be running, and then other things will be happening. So every process will get a chance to use the CPU. Okay, so in that case, it won't cause starvation over here. Priority scheduling, say if there is a process PI and then there is a process PJ. At this moment, say PI is having more priority than PJ. Okay, so PI will be running on the CPU. Say in future, another process is coming PK who is having more priority than PJ. So in that case, also what will be happening? Priority scheduling, like in that case, PK will be getting a chance to use the CPU. So as you can see, if high priority processes are coming, then low priority process will never get a chance to use the CPU. So that's why in that case also it can cause starvation. Shortest job first. Let's say if there is a process pi, pj, pk, okay, so if there are some processes running, so every time if new process comes with having short lesser burst time, so that process will be allowed to use the cpu. So if a process is having larger burst time, so it won't be allowed to use the cpu, like can potentially cause starvation. So hence D option is also correct. So someone might disagree that why A is incorrect, why A is correct. So Gate has given both the answers, A, C, D and C, D. Who has done any of the two, they are correct. Okay. So yeah, no need to worry about that. Yeah. So next question is related to semaphores. Okay. So now consider two functions, increment and decrement shown below. Okay. So wait and signal we are using. So there are 5 threads, each invoking increment one, like increment, like as you said, as you can see, like it's incrementing by 1, and here decrement function decrementing by 1. But this increment and decrement, they are surrounded with the semaphores, up and down operations. Okay, so what they're saying, and 3 threads each invoking decrement once on the same shared variable x. Now the initial value of x is 10. Initial value of x is 10. Okay, now suppose there are two implementations of semaphore s as follows. S is a binary semaphore initialized to 1. S is a counting semaphore initialized to 2. Okay, so now the question is, let v1 v2 be the values of x at the end of the execution of all the threads with the implementations i1 i2 respectively. Okay, so which one of the following choices correspond to the minimum possible values of v1 and v2 respectively? This is the question. Okay, come on, can we think about it? See, if it is a binary semaphore, can I say that there will be, like, if you're considering this as a critical section, and if it is a binary semaphore, so can I say that at a time only one thread will be allowed uh, to perform either increment or decrement? Means what I'm saying, that when using binary semaphore, can there be a possibility that one thread is executing increment operation at the same time another thread is executing decrement operation? Is it ever possible, guys? When we are talking about implementation 1 and S is a binary semaphore, is it ever possible? No. Why? See, when I'm doing down, see, to enter into the critical section, first we have to perform the down operation. Okay. So initially S value was 1. Initially S value was 1 and we are doing down operation. So weight of 1, so we are down. Okay. Now if another, so S value is 0, you can think. So now if I'm doing weight of 0, let's say one thread enters in the critical section. So this is thread 1. Okay. Now let's say thread 2 want to enter the critical section at this moment. So is it ever possible? he will be doing wait of s. So s value is 0, so it will be blocked. So this thread will be blocked. Okay, so in this case, yeah, that's why it's not possible. So every time only one thread will be inside, like only one thread will be executing either increment or decrement, but not simultaneously. Okay, so there are 5 threads, each invoking increment, and 3 threads invoking decrement. So can I say, if it is a binary semaphore, so what will be the minimum value of x? Like considering all the scenarios? Yes, you got it correct. So 5 threads, each invoking increment once, right? So 5 times incrementation will happen. So 10 plus 5, 15 will happen, and 3 threads are decrementing. So 10 plus 5 minus 3. So 12. So can I say 12 is the minimum answer? Yes. Okay. And what about maximum? Maximum will also be same. Why? Because as I said, only one thread will be allowed to execute the critical section. Okay, so at a time. Yeah, so that's why either you can ask minimum or maximum. For the implementation one, it will be 12. Okay, yeah. So now let's talk about if it is a counting semaphore. Okay, now if it is a counting semaphore, students, if it is a counting semaphore, how we can handle? Counting semaphore. Now I would like to ask one question. If S is a counting semaphore initialized to 2, so how many threads can at a time enter the critical section? Come on, how many threads can enter the critical section at a time? Yes, you got it correct. So 2 threads can be simultaneously accessing the critical section. Okay, so what will be happening in this case? Just a moment, students. Yeah. So if S is a counting semaphore whose value is initialized to 2, so there are 2 threads which can enter the critical section. So now let's talk about how it can happen, like how these things are happening. So any idea, students, how increment and decrement happens? So let's say if I'm doing x is equals to x plus 1, so how it will be happening? First, we will be loading this value. So let's say there's a register R1 and we'll be loading this value into R1. Then we'll be performing the increment operation, and then we'll be storing like R1 into X. This is how increment operation will happen. Okay. Similarly, if I'm doing the decrement operation, so decrement, how it will happen? First, again, I will load this value. This is some another register R2 or some any Rn register. Okay. Then I will perform the decrement operation, and then I will store it. Okay, so this is how increment and decrement operations happen over here. Okay, so now the context here, the students, is that what do you think? What can be the minimum value? What can be the minimum value of x? So if you see, maximum value will be always maximum and minimum. We'll try to discuss both for the implementation too. Okay, so how these things will be happening here is the following. See, I have a statement 1, I have a statement 2, I have a statement 3. Okay, so now in this case, how many semaphores we are having? Like we are having semaphore initialized to 2, so 2 threads can be executed simultaneously. So 5 threads are invoking once and 3 threads are invoking decrement. Okay, so 5 threads are invoking increment operation, and 3 threads are invoking decrement operation. Okay, so now the context is that 2 threads, when I say 2 threads can execute simultaneously, okay, 2 threads can execute simultaneously. Why? Because of binary semaphore having 2 values. Counting semaphore value is 2. Okay, counting semaphore value is 2. So now how we will be doing? So, okay, so let's discuss about the various scenarios how it is possible. So one thing is like if only one of the thread is executing critical section at a time, so we know in that case the answer will be like just loading, incrementing, and store every time. This will be happening. Okay, so in this case, the answer will be what? As discussed, it will be 12. If it is a very happy case, every time only one thread is executing, so in that case, the answer is 12. Okay, just now we saw 5 increments, 3 decrements. So effectively, 2 value will be incremented. So 10 plus 2, 12. This will be happening. Okay, now let's talk about what can be the actual minimum value possible. Okay, so let's discuss this scenario. Let's say there are two, let's say decrement threads. So let's say we have a decrement thread 1 and we have a decrement thread 2. Similarly, we have increment thread 1, increment thread 2, increment thread 3. Like we are having like this. Okay, so what I'll do is the following. See, initial value of x is 10. Okay, so now we can perform two decrement operations. So yeah, so what we'll do, first we will first let's say thread d1 goes, it will execute. So x value is 10, it will decrement it to 9. Okay, let's say here decrement happens. So let's say decrement r2. So now r2 will be having the value 9. But before executing this third statement, it got preempted. Okay, it got preempted. Okay, so not preempted, let's say it has returned to x. So let's say x value is 9. Okay, x value is 9. Again, let's say another thread come. So now 9 value will be changed to 8. Okay, so now in this case, what will be happening? X is equals to x minus 1. So how will it be happening? It will be loading the row value to R2. So R2 will be having 9. So 9 will be changed to 8 in this case. Okay, now what will be happening, that we are storing it. So 8 will be storing it in the variable x. Okay, so but before doing this third operation, it gets preempted. Okay, which second thread. Now all the threads will be executing this value. So x is equals to x plus 1 and all these things they will be doing. So let's say x value was what, 9. So 5 threads will be executing. So let's say all the 5 threads will perform the increment operation. So 9 value would have been updated to 14. Okay, but when all these 5 threads has been incremented by 1, now we are doing this third operation, store r2 comma x. So r2 was having the value what, 8. So 8 will be returned to the x. Okay, 8 will be returned to the x. So that's why in this case the minimum value can be 8. Okay, so come on, sorry, so there are 3 threads over here which are doing the decrement operation. If there would have been 2 threads, um, there are 3 threads, students, over here which are decrementing. Similarly, we can perform one more decrement over here, and in that case the value of, instead of 8, the answer would have been 7. Okay, I hope this is very clear. So you can simply perform this task. So again, if it is not clear, so how these things happen is like, again we are having d1, d2, d3. Okay, so these are decrement threads, you can say. Okay, and then we are having I1, I2, I3 up to I5, they are increment threads. So how we got that values is the following, that first make the two decrement threads execute. So execute d1, d2. So in that case, x value was initially 10, now it will be x is equals to 8. Okay, so now let's execute d3 thread, but make preemption before the final store, just before the store operation. Okay, just before the store operation. Now after this, what we'll do, we'll make all the up to I5, we'll make all this increment threads execute. Increment threads, make them execute. So in this case, what will be happening, that 8 plus 5, 13. So value of x would have become 13. I hope it's very clear till now. Now what we'll do, make d3 thread execute store operation. Okay, d3 thread execute store operation. So what was the value store operation would have in this point? A, like initially it would have been 8, but d3 when it would have executed just before the store, in that register the value would have been 7. Okay, so yeah, so we will be writing that value of x to 7. So x is equals to 7, that's why it's coming. Okay, so in this case, I'm saying, students, in this part, when we are doing, so what would have happened, that x value would have been still 8, but at the register level, any register level Rn, this value would have been 7. So when we are doing store operation, so Rn comma x, that we would have done. So what would have happened then? Rn value would have come to x over here. So that's why value 7 would have come. Okay. Yeah. So that's why in this case, the answer is C. Correct? Yeah. Come on. Let's discuss another, students. Let's see another question, students. Read the question. Yeah. So what we have been given? We have been given a 2D array. Okay. 2D array we have been given, which is of size of 128 rows and 128 columns. Okay. So now, which is an integer array. So what they are saying, that all these elements, they are stored in a row major fashion. Okay. They are stored in the row major order. Now they're saying that like they have designed system in such a manner that each page can store 512 elements. Okay, each page can store how many? 512 elements. So now they are using LRU page replacement policy. They are using LRU, and what they're saying, that they have total 30 physical page frames. 30 physical page frames. Okay, now what they are saying is the following, that now they are accessing the elements. I hope we have clearly observed that we are elements stored in the row major order, but we are accessing it in a, accessing of the elements are happening in a column major. Accessing of elements are happening column wise. Yes, column wise. Okay. So now the question is, given 30 physical page frames I am having, the number of the page faults generated during the execution of this code snippets is, that is the question. Okay. Now let's try to read this. Let's try to read the question, students. So each page can store 512 elements. How many rows I'm having? 128. So each row can store 128 elements, and each page can store 512 elements. So can I ask, each page will store dash number of rows? Come on. Each page will store how many number of rows? Can I say 4? Because each row can have 128 elements, and total number of elements a page can have is 512. Okay, so how much it is? 128 is 2 power 9 and it is 2 power 7. So 9.2, that will be 2 power 2. So 4 rows. See, each page we can store 4 rows. Okay, now I hope it's very clear. So what I want to guys to visualize is that, let's say I'm having 0, 1, 2, 3. So first 4 rows will be stored in page 0. Then 4, 5, 6, 7 will be stored in page 1. Okay, then like this it will be happening. So then it first page 0, then page 1, then 8, 9, 10, 11, like this will be stored in page 2. I hope you are getting the picture. Okay, so similarly, like these are the row number. Okay, these are the row numbers. Okay, yeah. So now what will be the last case? It will be 124, 125, 126, 127. Any idea where this will be stored? Come on, this will be stored at where? Think. So these are the rows number. Okay. So again, I'll to make you help more better, like 120, 121, 122, 123. Okay. Then again, I'll write just one more step here. So it will be like 116, 117, 118, 119. Okay, these are the again rows number we have written. Okay, so can I say students that this will be stored in page 29? Do you all agree with me on this? Come on, students, do you all agree? See, we have 30 physical page frames. Okay, so we are starting with 0, 4, 8. So if you will check, like we have 120 rows. Each row can store 4 elements. So 120 by 4, 30. So 30 pages from 0 to 29 it can be stored. Okay, now let's see how these things will be happening. So first, let's say like for first access, let's say first access will be what? Can I say 0 comma 0? So it will be accessing the 0th row. So initially 0th row won't be in my physical page frame, so I'll be getting a page fault. Okay, so for d of 0 0, there will be a page fault. Do you all agree? Yes. Now next will be what? Will it be 0 0 or like 0 1 or 1 0? It will be 1 0, right? Because we are accessing in the column major. So for 1, will it be a miss? Like, will it be a page fault? No, because in that time it will be in the memory. Similarly, for 2, will it be a page fault? No. For 3, will it be a page fault? No. Okay, I'm writing it again. Okay, so in this case, page fault, in this case, it's not a page fault. In this case also, it won't be a page fault. Okay, I hope it's very clear, students. Okay, but when I will be accessing D of 40, will there be a page fault? Yes. So now page fault will be happening like this. Okay. So like this, it will be happening. So again for 5, 6, 7, there won't be a page fault. Then for 8 will be a page fault, but 9, 10, 11, it won't be a page fault. Okay. So in this manner, I will be storing the elements. Like I'll be getting the page fault. So now let's come to the tricky part. When I'm accessing D of 120 comma 0. Okay, come here. D of 120 comma 0. So what I would like to have is like 120th row and 0 column. So how many physical page I am having? I have total 30. 30 like starting from 0 1 all the way up to 29. Okay, so these many page frames I am having, but at this moment all the frames has been occupied. But when I would like to have access 120th element, so how many like now I have to apply page replacement policy. Okay, I have to apply page replacement policy. Why? Because I don't have extra space to put a page into the memory, so that's why I have to replace a page. So since it is a LRU policy that we are using, so which page I should replace? Which page I should replace, students? Can I say I should replace page 0 because it's least recently used, because the first time it was accessed, then later point of time page 1, then page 2. Okay, so that's why this will be replaced. Okay, so what will be happening, that 120, 121, 122, 123, this will be coming over here. 120, 121, this will be coming over here, and then this guy will be coming, this will be having what? Last set, 124, 125, 126, 127. This will be happening over here. Okay, so this also will be having page fault. So can I say, students, can I say, please always on the screen, so when I'm just doing this inner for loop, so how many times page fault happened? How many times page fault happened? Can I say for 4 rows? For 4 rows, one page fault happened. Okay, so how many rows I'm having? 128. So how many page faults? How many page faults, students? Can I say 2 power? 128 by 4. So this is 2 power 7 by 2 power 2. So how many page faults? 2 power 5. Do you all agree? So now let's try to have the second iteration. Second iteration, what will be happening? I equal to 1 and then j is equals to 0. So in this case, what will be happening? I is equals to 1, j is equals to 0. So in this case, I'm trying to access second column. Second column and this level. So it will be d of ji. So it will be like um, accessing the second column. So second column will be what? Again 0, 1. Like I would like to access first row, second row like that. So will 0, 1, 2, 3 elements are present here? No, because that was being replaced by LRU. So now, according to the LRU, which page I should replace? This page I should replace. So I hope you got the picture. What I want to emphasize is that for each of the iterations, every time page fault will be happening. So for the 4 rows, there will be one page fault. Okay, so can I say students here, please always on the screen. So for like outer loop is executing how many times? 128 times. And for each of this inner loop, how many times page fault is happening? 32. Okay, so that's why these many page faults will be happening. So 128 into 32. Okay, so what is the answer? 2 power 7 into 2 power 5, which is 2 power 12. Hence 4096. So the number of page faults that will be happening is 4096. Okay. Yeah, let's discuss the last question related to the operating system in the previous series that has come. So now consider a computer system with 57-bit virtual addressing using multi-level tree structure page table with L levels for virtual to physical address translation. The page size is 4 KB and a page table entry at any of the level occupies 8 bytes. So what is the value of L? Come on, students, think. Why we do multi-level paging? To make sure that my page table is fit into one page. Okay, my page table should fit into one page. So for that, I'll use page tables. So page table entry, if you talk about typical page table entry, so how does it look? It has uh, like it has some size. So like it will have the corresponding virtual address, physical address, and then it has been mentioned that the page table entry at any other level occupies 8 bytes. So if each of the page table entry has 8 bytes and I would like to keep page table size, page table size as 4 kilobytes. Okay, so how many entries I can have? See, one entry is having 8 bytes and page table size is 4 kilobytes. So what is the total number of entries in the page table? So total number of entries is equal to 4 kilobyte by 8 bytes. So this will be 512. Okay, so 512 means 9 bits. Do you all agree? Do you all agree, students? I hope it's very clear. What we were discussing, that page table entry is 8 bytes and page table size is 4 kilobytes. So if I'm doing multi-level paging, again, what is the high-level logic of multi-level paging is that let's try to keep the the upper limit of page table size should be not more than the page size. Okay, so page table, like this is the page size. Okay, this is the page size, and like you can also say page table sizes should be equal to the page size. Okay, so we are having this page table size is equal to page size. So that we are doing. So we know, right, at high level how is the addressing works. Like if I'm having 57-bit, okay, 57-bit I'm having. So page size is how much? Page size is 4 kilobytes. So 4 kilobytes means how many bits, students? 12 bits. So can I say 57 minus 12? So this is the 45 bits of like this many virtual addresses I'm having. So 2 power 45 addresses I'm having. So if I would not have used multi-level paging, so how would have happened? It 2 power 45 into 8 bytes of page table entry. So these many will be the size of page table, which we can't afford. So that's why we are going for multi-level paging. Okay, so yeah, so we have 57 bits. So now again, now we'll be doing multi-level paging for this 2 power 45 virtual addresses. So again, as discussed that we will be requiring 9 bits uh, for one level. So just try this is 45 9. So 45 minus 9 is how much? 36. Okay, so 36 will, if we'll do still 2 power 36 into 8, so it will be more than the page size. So again I will divide. So 36, again I'll divide it into 9. Then similarly 27. So like this it will be happening. Okay, so how many bits I'm having? 999 and then another 9. Okay, so how many levels I got, students, over here? Come on, is it 5? Is it 5? Come on. Come on, students. Your response means a lot to me. Is there anything that we are missing? See, page table, each entry occupies 8 bytes. Okay, and what is the page table size? Page table size should be equal to the page size. So, yeah, that's the case. Yeah. So we are having 57 bits. So every time how will be happening is like this is outer page table, then inner, then inner, then inner, then inner. So I hope you got it, that how I have, like, we are having 45 bits over here, so how we are beautifully divided into the 9, because every level will have 2 power 9 entries only. Okay, I'm writing every level of page table, every level of page table will not have more than 2 power 9 entries. So that's why I just writing it by 9. So 9, 9, 9, and then 9, and then 9 over here. So that's why we are maintaining that everywhere 2 power 9 entries are there, and each entry is occupying 8 bytes. So this will be equal to 2 power 12. So it's occupying the 4 kilobytes. Okay. So again, so the answer for this case is how many levels? 5 levels. Is it clear? Yeah. The answer is 5. Yes. Okay. Yeah. So now let's discuss the questions related to computer networks. Okay. Let's read this question. I'll be back in a minute. Try to read this question. Just a minute, students. Right. Recording. So now let's assume, let's discuss the question. Suppose two hosts are connected by a point-to-point link and they are configured to use stop and wait protocol for the reliable data transfer. Identify in which of the following scenarios the utilization of the link is the lowest. Okay, so we all know the efficiency for the case of stop and wait. How stop and wait works? Any idea? How stop and wait protocol works? Think, students, think. We have two things. Let's say client and server. Okay, so client will send something, he'll get an acknowledgement, then only client will send other data, then acknowledgement, then client will send something, acknowledgement. So it means after the client receives the acknowledgement, then only he'll send the next data, or he'll wait some time. If he doesn't receive that response, then it will proceed. Okay, so yeah, so what is the efficiency for the case of stop and wait protocol? What is the efficiency of stop and wait protocols? It is like, come on, what is the efficiency of transmission? In this case, it is transmission time by plus this guy. Okay, so now if you will divide by relevant values, so let's say this is 1 by 1 plus 2a, where a is equals to tp by tt. Okay, yeah. So now, yeah, so what is the value of tp, students? Come on, what is the value of tp? It is like, can think it's distance by velocity. Okay, now what is the value of tt? It's like length by bandwidth. Okay, so it will be like tp by tt. So let's put over here, so it will be like 1 by 1 plus 2 into distance by velocity divided by then length will come here, and then bandwidth will come here. Okay, so yeah, let's see the options. It's like longer link length and higher transmission rate. So to have efficiency as smaller, can I say this guy has to be bigger? This guy has to be bigger, yes. So can I say bandwidth? So this denominator should be more. So can I say bandwidth should be more? Yes, and distance should be less. Yeah, distance should be more and the other part. So that's why B is correct. Okay. Sure. Next question, students. Which of the following statements are incorrect about the OSPF routing protocol? Come on, students. OSPF. Come on, any idea how OSPF works, students? Okay, let me put in this manner. Is OSPF interdomain or intradomain? So again, it's a routing protocol. So it's just transfer the data among the routers. So OSPF is intradomain. Okay, this is intradomain, students. So this is an incorrect option. Okay, so this statement is incorrect. Okay, come on. OSPF uses Bellman-Ford or Dijkstra. Come on, students. OSPF uses which algorithm? Think. OSPF uses Bellman-Ford, okay, to find the shortest path. So yes, this is correct. So again, this part is incorrect. Okay. So OSPF implements hierarchical routing. Yes, this is correct because they use area 0. So that's why it's a hierarchical routing. Okay. So yes, the correct options are B and C. Like which of the followings are incorrect? So B and C are incorrect. Hmm. Come on, next question. Suppose you are asked to design a new reliable byte stream transport protocol like TCP. Now, this protocol named MyTCP runs over 100 megabits per second network with round trip type of 150 milliseconds, and the maximum segment lifetime is of 2 minutes. So, what can be the valid length of the sequence number? Let's see, students. So, we are having 100 megabits per second. Okay, 100 megabits per second. So this is the bandwidth, means in 1 second how much I can transfer? 100 megabits. Okay, 100 megabits I can transfer. So what is the maximum segment lifetime of, like, they are given maximum segment lifetime of 2 minutes. So can I say in 120 seconds how many data I can transfer? It's like 100 megabits into 120. Okay, there's many things I can transfer, there's many bits is there again. So how many bytes I can transfer in 120 seconds? It's like 100 MB. Okay, 100 MB. Again, MB you can think of it as like a 10 power 6 into 120 by 8. Okay, so this is the value. This many bytes I can transfer. Yes. Any doubt so far? So if you rearrange, so this value will be what? So 100 into 10 power 6 into 120 by 8. Okay, so this will be, we can rearrange this 1000 into 10 power 6 into 12 by 8. So this is 125. So 125 into 12 if we will do, okay, this value if you will calculate, so this is this many bytes we can transfer. Okay, yeah. So when you will take the log, so sequence number is what? Sequence number, like the number of bits, is always greater than equal to log of this value. Say this value is v, so log of v we will be calculating. Okay, so yeah, so what, so if you will take the like log of this guy, 125 into 12 into 10 power 6, so this value will be what, like again this is like maximum of this. Yeah, so this will be greater than equal to, so if you will try to compute this value, so this value will be coming somewhere around, I think 31 point something. So yeah, so I think this value will come somewhere around 30 point something. Yeah, 30 31 you can compute this value. So somewhere comes around 31. Okay, so which are the options that are correct? So B, C and D. Okay, so these are the correct options for this. Any doubts, please let me know. I'm waiting for a minute. Okay, so to be precise, this value will be coming more where around 30.48. Okay, so hence number of bits should be greater than equal to 31. So greater than 31, whatever the options, that will be correct. Okay, so yeah, in this case we have given this round trip time value, but that was not required. Okay, this was like just for giving extra information. Okay, come on. Yeah, this question is related to the DNS part. Come on, let's read it. So what they've given, like suppose in a web browser, you click on this link gate23.in in the URL. Okay, now the browser cache is empty. The IP address for this URL is not cached in your local host. Okay, means it's not present in my local thing. So a DNS lookup is triggered by the local DNS server deployed on your local host over three-tier DNS hierarchy in an iterative mode. Okay, no resource records are cached anywhere across all the DNS servers. Okay, so it means when you do this three-tier DNS hierarchy in an iterative mode. Okay, so what does this mean? Okay, let's read the question completely. Let RTT denote the round trip time between your local host and the DNS server in the DNS hierarchy. Okay, so I have a local host. I have a local host. Okay, I have a local host, and then I'm having a web server. So yeah, I'm just saying. So let's say this is my web browser. This is my web browser, and DNS servers. Okay, so there can be multiple servers. Okay, so what they are saying, denote the round trip time. They denote the round trip time between your local host and DNS servers in the DNS hierarchy. So the round trip time between the local hosts and the web server hosting is also equal to RTT. Means if I'm hitting this, once I got to know the IP address, so hitting the website and getting the details, so this also is like round trip time is RTT. Okay, yeah, so now the HTML file associated with the URL is small enough to have negligible transmission time and negligible rendering time by your web browser, which references 10 equally small objects on the same web server. Okay, now which one of the following statements is are correct about the minimal elapsed time between clicking on the URL and your browser fully rendering it? I know this question has been asked more into the this part in depth of DNS. Okay, so yeah, let's think. I'm giving you a time to think about it, how we can solve it. Yes, students. So yeah, we are back. Yeah. So in the question, what they are asking that which of the following statements is are correct about the minimum elapsed time, between clicking on the URL and your browser fully rendering it. So what is the meaning of rendering it over here? That we have to give 10 equally small objects. So what is the overall time taken? And again, in the options, what does it means? We have parallel TCP connections and we have connections with pipelining. Okay, we have parallel TCP connections and HTTP with pipelining. Okay, so with pipelining, okay, so let's talk about how these things will be happening. So what initially what is happening that if we are not having the IP address for the given URL, so how much time will it be getting to fetch the time for the corresponding URL? like if I'm having IP address, okay, let me write here. Hmm. So how much is the time, like the time taken to get IP address from URL is get IP address from URL is dash. In this case, the answer will be 3 RTT. Why? Because we are having 3-tier DNS hierarchy in an iterative mode. Okay, so this is iterative mode, students. So it's like one by one we'll do, and then we'll get the time. Okay, so how much is the time required? In this case will be 3 RTT to get the this part, fetching the URL, like getting the IP address. Okay, now what will happen is the following. Let RTT denote the round trip time between your local host and the DNS server in this hierarchy. Okay, so now everyone knows how like HTTP connection works. So let's say if this is client, and this is server. How it will be happening? First, I will be sending the request. Like I want to maintain a connection. Then server will send, okay, let's connect. I would also like to make it connect. Then he will be requesting, and then he will be getting the actual data. So how many request time? This is RTT. This will also take another RTT. Okay, so 2 RTT will be required. 2 RTT will be required for establishing connection. Okay, so 2 RTT will be required for establishing connections. Okay, so it's you remember, right? It's like a three-way handshake, or like, so not three-way, it's like a two-way handshake. Like client is also sending, then server is also happening. Okay, yeah. So once this is happening, so so 2 RTT is required for establishing connection, 3 RTT is required for getting the IP address. So that's why it's like 3-tier. Okay, now what they are doing, now let's check out the options. So what they're saying, with 5 parallel TCP connections, how much we can do. So once this is connection is established, now we are having parallel TCP connections. Okay, what they're saying is the following, students, that how much is the time is been taken for the non-persistent, okay, with 5 parallel TCP connections. So I'm having non-persistent with 5 TCP parallel connections. So if I'm having parallel connections, students, so how many objects I have to retrieve? I have to retrieve 10 objects. Okay, so how many RTT will be required? Like in first, like in, since it's non-persistent, so for every object, I have to establish a connection. Okay, do you all agree? So for non-persistent, we have to establish connection, to establish new connection for every object, for every new object. Okay, so now what will happen in this case? It's a non-persistent, we have to establish connection for every new object, but since it's a parallel connection, so can I say for each connection, like 3, 4, 5, I can retrieve all the 5 objects? Yes. So can I say in one connection, in one RTT, I can retrieve 5 objects. So in 2 RTT, like 10 objects can be retrieved in 2 RTT. Okay, so this is for just for retrieving, but we have to establish the connection. For establishing the connection, how much time it will take? Another 2 RTT. So can I say that for parallel TCP, for parallel connections, like for this scenario, like non-persistent HTTP with 5 parallel TCP connections, how it will be happening? That first 3 RTTs are required for getting IP address. Okay, 3 RTTs are required for getting IP address. Okay, then what will be happening, students? 2 RTT will be required for getting the web page. Okay, so this is common. Okay, Now, after all this, can I say 2 into 2 RTT will be required for fetching 10 objects? Do you agree? Do you agree for this parallel TCP connections? Why? Because for non-persistent, we have to first establish a connection also. So that's why we have an extra 2 RTT. Just now we saw, right? Two-way handshake, like in this case, how it will be happening? Yeah. So total how much? 3 plus 2, 5 and 5 plus 4, 9. So 9 RTTs are required in the case of non-persistent HTTP. Is it clear? Is it clear? With 5 parallel connections. C is correct. But now with the case of pipelining, it's a persistent. So we don't need to establish new connection. With pipelining, what happens that, again I'm writing, with pipelining, in one request, we can send, we can request for all 10 objects. Okay. So in this case, what will be happening? We can request for all the 10 objects. So 3 RTTs for getting IP address, 2 RTT for getting web page, and one more RTT for just establishing the getting the 10 objects. In this case, 6 RTTs we have got. Okay. So yes, for this case, answer is C and D. Correct? Yeah. One last question, students, for the computer networks as asked in the previous year. It's regarding the subnetting. Come on, let's try. The forwarding table of our router is shown below. Okay, we have been given a subnet number, subnet mask, and interface ID. So a packet addressed to the destination address arrives at the router. So it will be forwarded to the interface with the ID match. So we all know the interface, like it will go to which interface, right? So what we'll do, we'll have a given IP address. So we'll do the logical AND with the subnet mask. Okay, so we'll check that whether it is mapping to any subnet number. If it is only one subnet number, then we'll go to that particular interface ID. Otherwise, what will be happening? Just a moment, students. Yeah. Otherwise, what will happen that it will be forwarded to the interface. Yeah, if there is more than one match, then we will go for that subnet number whose subnet mask is having more number of ones. Okay, so yeah, let's go one by one. So we are having 200.150.68.118. Okay, so if I'm doing 255.255 means all are ones, so it will be as good as 200.150.0.0. So yeah, this is matching. Okay, similarly, 200.150.64.0, like this is the with this guy. So again, 224 is what, having both the values as 1. Okay, so is B is matching, students? Is B is matching? Think. So see, we know 200 and 150 will match. 224 is what? 128, 64, 32. Okay. So can I say that this will also match? Yes. So B is also matching. Okay. Similarly, 255, 255, 255. Is this matching? Is this matching, students? All are ones. So yeah, these are also matching. Okay. Is D is matching? No. Okay, so D is not matching, students, in this case. Yeah, so again, as we got more than one matching, so we check that whoever subnet mask is having more than number more ones, it will go to that part. So in this case, it will go to which interface, students? Yes, it will go to interface ID 3. Okay. Yeah. Yeah, so thank you, students, for joining. I hope this class was fruitful and you learned something new. Okay, so I wish you all the best for the gate exam, and yeah, take care. Thank you for attending this class. Yeah, bye.